Hello and welcome to Monday's edition of Cracking the Cryptic, where as 2025 approaches rapidly, we have a puzzle that celebrates that and celebrates a very unusual property of 2025, which is something I have referred to in some of the Christmas cards I sent this year. Anyway, the puzzle on the screen is called The Secret Squared. It's by BenTen. It's been recommended to us a couple of times of late, including overnight last night by none other than Michael Lefkowitz, the brilliant constructor juggler, of course. And why is this puzzle called The Secret Squared? Well, those of you with a mathematical bent may know that 2025 is an unusual year because it is a square number. And what is it the square of? Well, it is a square of a Sudoku secret, something I share with only my very favourite people. And if you're still watching the channel, if you're still watching this video, you're definitely one of my favourite people. The secret is, of course, that all of the digits in a box or a single column or a single row of Sudoku sum to 45, and 45 squared is 2025. We need to put this on a t-shirt, something like 45 square. We should say it's 45 squared. If you know, you know. Or, so I don't know, the secret squared. It's the secret squared. If you know, you know. Anyway, let us know what we should put on the secret, because my ability to write catchy phrases is limited, as you've no doubt just noticed. But this puzzle, it appeals to me greatly. It's some sort of region, some lines with multiplication. That is what's going on. I don't know how hard it is. No one has told us. So I'm taking on trust of the recommendations that it's going to be suitable for a video. And I will read you the rules in a moment or two's time. Now, what else should I mention today? I'm recording this video actually slightly earlier than usual because I have what I hope will be one of life's great treats to attend this evening, when I'm going to go and watch Oliver in the West End. Oliver is my favourite musical, yeah, there is a new West End show of Oliver, and I've managed to get some tickets, so that is where I shall be when this video goes live, hopefully. Yes, I hope it will be rather more successful than one of the last times I went to the theatre, which was to watch The Curious Incident of the Dog in the Night Time, and the theatre fell down. So almost literally the roof fell in as we were in the audience. It was quite terrifying. You can still, if you search online, where was that? I can't remember. I can't even remember now which theatre it was. It was probably 10 years ago. But it was one of those moments where life flashes before your eyes, because you don't expect to be in buildings when the roof falls down on you. Anyway, hopefully that won't happen this evening, and that is why I'm recording this slightly earlier in the day than usual. And that's a total digression. But let me talk to you about other things. We have some big news on the 1st of January. If you're a patron of the channel, we have this wonderful new Sudoku hunt, a late Christmas present for you all. The Hobbit by Blobz. 19 puzzles themed around Tolkien's book. Absolutely fantastic stuff. Look out for it. 4 p.m. UK time is when it will go live on the 1st of January. I can't commend it highly enough to you. And I have had an email from the winner of this month's competition. So I'm hoping that Cecilia and I will get together and make another viewer video as the prize for December. So look out for that video in due course. Now let's do some birthdays as well. I have 2 birthdays today. We'll start off with Casey down there in Sydney, Australia, but maybe on holiday in Tasmania over Christmas. I'm not sure. But Casey, you've turned the big 3-0 today. And I know this because your wife Agnes wrote to us and told us you've been watching since COVID. So thank you for doing that. And apparently you enjoy battling with Mark over the Wordle in the Minute. Oh, my friend John. Oh, well done. I don't know. John, I've got a great golfing friend, John, who sometimes watches the channel. And messaged me this morning to show me the result of Wordle, which I haven't done yet, but he got Wordle in 1 Apparently he's been selecting the same word ever since Wordle started, and today it came up trumps. So John, well, congratulations, and congratulations Casey, obviously. And then the other birthday is Odette. Odette, what a lovely name. Your niece Iona wrote to us and asked for a wee shout out, so I'm very happy to do that. And Iona told us that you really enjoy watching. So Odette, thank you very much for watching. I hope you have a brilliant birthday too, perhaps with a large slice of chocolate cake. Now, let's have a look at some Sudoku solving, and we will have a go at The Secret Squared by BenTen. These are the rules. We've got normal Sudoku rules apply, and that means we have to put the digits 1 to 9 once each in every row, every column, and every 3x3 box. Each 3x3 box contains a circled digit, which is equal to the multiplier of that box. The multiplier applies to all cells of the box it lies within. The value of each cell is equal to the digit placed in the cell multiplied by the multiplier of its box. Well, that sort of makes sense, doesn't it? The given cage total, which is 2025, shows the sum of the values of all cells within the cage. That's all 81 Sudoku digits. Yeah, actually, yeah, 2025 must be divisible by 81. Sorry, I was just thinking about thinking nonsense. But anyway, let me not get distracted. Now, the given cage totals, we've done that rule. Okay, and then it says box borders divide the blue lines into segments whose values have the same sum. Different lines may have different sums. So these are region sum lines, but with this weird twist. Because what are we saying here? Let's look at this pyramid line. You put a number in there. Let's just put a number in. Let's put 5 in there. And you're saying then that the numbers on this line, which include the number 5, all get multiplied by 5. Okay. And those, and that line, obviously, the box borders divide the line. So those 3, those 2, and that 1 are all different segments. Oh, I was going to say that one doesn't get a multiplier, but it does, doesn't it? That one will be multiplied by that one. No, this is confusing, actually. So you have to... So the greens get multiplied by 5. The oranges get multiplied by whatever that number is. And the blue gets multiplied by whatever that number is. And in each case, the number should be the same number. So the greens add to x, say, or not add to x, but when multiplied by 5, add to x. And then the oranges multiplied by that digit add up to x. And the blue multiplied by that digit add up to x, when we don't know what x is. Wow. Do have a go. The way to play is to click the link under the video as usual. But now I get to play Let's Get Cracking. And okay, there's one thing that I think must be true in this puzzle. That because 2025 is 45 squared, and each box adds to 45 because of the secret, it must be true, mustn't it, that the sum of all the circles, of which there are 9, must be 45. Because we need to multiply... Yeah, let me just think about that. So let's say that number is a 6. That's saying that the sum of all the digits in that box is 45 times 6. Yeah, that's right. So if this was a 5, that would be 45 times 5. And we need to do that such that these circles sum to 45. So in the end, the whole grid sums to 45 times 45, which is the 2025 that we need. Now, the reason I think it's very interesting that there are 9 circles is because that heavily suggests to me that these circles will be the digits 1 to 9 once each, because we know from the secret that they sum to 45. Now, I'm just going to, I think the rules don't say that, because presumably you're meant to just appreciate it. But I think we'll find that these numbers are all different. Now, having said all that, do we actually know anything? So, okay, there are weirdities going on here. Oh, yes, okay. So I was going to say this tiny short line here might be interesting, because obviously what we're saying is this cell multiplied by that number is the same as this cell multiplied by that number. Yeah, that's just not helpful. I'm sorry, that's not helpful at all. What about the great long line then? That encompasses a whole 45's worth of digits in box 5. Oh yeah, okay. There is no way. Yeah, this is a 1. That is the obvious starting point to the puzzle, because let's just consider this line. Obviously it's got 45's worth of naked digits upon it. And if this circle was anything other than 1, let's say it was 2, now the values of the cells in that box would be 90. And that's not going to work, is it? Because how could I make that single cell have a value of 90? Even if these were a 9-8 pair, 9 times 8 is only 72. It's not as much as 90. So I think that's got to be a 1. And therefore the value of this cell is 45. And that's very interesting, because 45 doesn't have that many dividers, does it? I mean, 45 is 5 times 9. Given we have to express it in terms of 2 Sudoku digits, we can't do 3 times 15, because we can't write 15 into either of these squares. It's got to be 5 times 9. That's the only way we can make it multiply. Now. Okay, and that's going to be the same here. They've also got to be 5 and 9. So what we're going to find is that for some reason these are different. And 5 and 9 will have then been used up in our circles. Now, what's going on in box 4? We've got the sum of these 2 digits is multiplied by this number to give us 45. Without using 5. And 5 is a prime factor of 45. So what that tells us, because I can't put 5 as a multiplier here, 5 must be a factor of the sum of these 2 digits. Yes, I think... Let's just think about it. I can't put 9 in here either. So the only prime factor I've got left is 3. So this has got to be 3. It can't be 3 times 3 because 9 has gone. And then these add up to 15 without using 9. So they are 7 and 8. And suddenly 2, 4, 6 is what we've got into the gaps in this row. And we've got 2 digits. We've got a 3 now in a circle. We've got no, I was going to say, how can that be a 2? Because those 2 have to add up to more than 2. But we're not talking, that's not how this works at all. This digit gets multiplied by that digit. And okay, and the sum of those gets multiplied by that, and that one is a square number, isn't it? Oh, okay. Yes. So doesn't that have to be 9? All I'm thinking there is that this is a square number because it's whatever digit this is, it's also the multiplier. So its value is a square. Now imagine this was 5. Then the value of this cell is either 10, 20 or 30, none of which are square numbers. So I think that has to be 9. 18, 36 is square, 54 is not square. So this has to be 9 and 4 to give it to. It's the only combination here that yields a square. That's a 6, therefore. That's not. Oh, this is great. That's a 2 naked single. Oh, this is gorgeous puzzle. What a gorgeous puzzle. That's a 6 by Sudoku. That's a 5 by Sudoku. And I want to write 5 in here now. I can't do it because we're not told explicitly that these are all going to be different, but let's just keep going with what we know. So we know 36 then is what's going on here. So if that was a 2, these would have to add up to 18, which is impossible. So it's more than 2. It can't be 3 by the secret, but let's assume it. Let's just check. If it was 3, these would add up to 12, which would be very possible actually. It can't be 4. I mean, again, it can't be 6 because the 6 is going to be repeating, but let's say it was 6. These would add up to 6. Yeah, see, that's also got options. I suppose as well that could be a 9, could it? I'm just trying to think of factors of 36 that we could write into this square. 7 and 8 won't work, so that is 3, 6 or 9. Very annoyingly, I'm not sure I can actually say which. I mean, obviously. Oh no, so it's. Oh, hang on. Hang on, I've already got 3, 6 and 9. Oh, that's really weird. Okay. I might have made a mistake with this, with pencil marking this, I think. 1 and 2 are factors of 36, but not that we can make this add up to a sensible total. Oh, no, I can't put 4 in because 4's ruled out by Sudoku. 36 is such a useful number. Oh dear, I haven't made a mistake, I don't think. But now what we're saying is it's still true that all the circles add up to 45, but they are not a set of discrete digits 1 to 9, one of each, because this is definitely a repeat. And that means that that one could be a 9 after all. Well, can we now do this one a bit better? It's 9 times something. No, I don't think that's very helpful actually. I mean, it could even be a 1 here, couldn't it? If that was a 1 and that was a 9, then that would multiply to 9 and that would multiply to 9. So that's not probably what we do next. It's going to be, I don't know. That digit is Sudokuable. 1, 2, it can't be 1. No, it can't be 1. By multiplication. All right, let's have a look at this digit. 1, 2, 4, 6, I think. And I can, but that's just because it sees a 7, 8 pair and it sees a 5, 9 pair and obviously sees 3 as well. Now, it can't be 1. In fact, it can't be 2 either, because those 3 digits, the sum of those digits will be 6. And then we've got to multiply that by that digit, which can't be a 1 either. So that this is at least 12 at the very minimum. If I put 1, 2 and 3 on that diagonal and then multiply it by the smallest I could, I get 1, 2, 3, which is 6, times 2 is 12. So this certainly can't be a 1 or a 2, because we're only multiplying by 3 here. 3 times 4 looks quite good actually, doesn't it? But the maximum is 18. So, what's this digit? If that's as much as 4, that's too much. It's way too much. No, 3 works. Okay, this is not 6, definitely. It's 2 or 3. If it's 4, the reason we can rule out 4 is let's add 4 to 1 and 2, which would be the minimum. These 3 digits add up to 7. Times 4 is 28, but I've only got a maximum here of 3 times 6, which is 18. If this is 3, then this has to be 3 would have to be 2 here and 1 here, because these would have to add up to 6. If this is 2, then it depends. We could be having a 1-3 pair if this is a 4, but if this is a 6 and we're going up to 18, these have to add up to 9, including the 2. So these would be... well, actually, I'm tempted to pencil mark this, because... Okay, let's do this. I'm just going to do this properly, because I've spotted something else now. Okay, so let's start off. If this is 3, the only way to keep to this could work is if this is 6 then. And these would have to be a 1-2 pair, which would be exactly in that order. If this is 2 though, we could have a 1-3 pair here, so we've got 6 times 2 is 12 if this is 4. So that would put 1 and 3 here, and a 3 would be added to this cell. But here's the complicated one. If this is 2 and this is 6, these 3 squares have to add up to 9, involving a 2 in the sum. So we're either looking at 2, 3, 4, so that would add a 4 to this one, and a 4 to this one, or we're looking at 1, 2, 6, which is impossible, because we can't write 6 into either of those squares due to Sudoku. So this is a bit restricted, but actually still not very good. I'm afraid it's not very good. I've done a lot of work there for nothing. Oh, Bobbins, I'm sorry. What on earth then? So, it's not very clear where else we look though. This is a really clever, it's a really interesting puzzle. I love it actually. It's really, really interesting in all the best ways. I've probably missed some Sudoku. What's that? If this was 18, oh, that's squared. Ah, oh, this is again interesting. Yeah, okay. So we can think about these 2 squares. Now, there are ways of thinking about it. One way would be that we sum those digits and then multiply that sum by the multiplier, which is this digit. But if I think about it slightly differently, we could think about it as this digit squared plus this digit times this digit. That's the other way of writing that sum. And what that has allowed me to appreciate is that this can't be a massive digit. Because let's say that was 4, then we know that the way this works is 4 squared, which is 16, plus 4 times this digit. Well, there's no way you can make 4, once you're at 16, you can't make that 18. It's not going to work. So that's got to be a maximum. We might be able to do better than this. Can this be 1? Oh, no. No, it can't be 1 because we're heading to at least 12. And we can't, it just doesn't work. This would have to be too big. So if this is 3, does it work? We have got a 2-3 pair here as well. If it's 3, we've got 9. Oh, you see, that would work. That would work with a 1 here. Works very prettily. So you'd have 3 squared plus 1 times 3 for 12. And if this was 18, that doesn't work then, I don't think. If this is a 6 and that's a 3, then you need 3 times something to equal 9, and I think that would put 2 3s in this box, so that doesn't work. But there are going to be other options. If this is 2, we've got 4. And then I want to say if that's a 4, it'll work. If this is 12, because we've got 2 times 4. Yeah, that's fine. That's definitely working. But what if this is 18 again? If this is 18 and this is 2, these have to sum to 9. That would be a 7 here, wouldn't it? So this is a snooker maximum. It's 1, 4 or 7. And that's not very good. That's not very good either. Okay, so we don't know how this works. We just end up with a 2-3 pair in the circles. Oh, thereby reinforcing the fact that we know that. I've got another idea, but thereby reinforcing the fact that we know that there are repeated digits in circles, because we've definitely got a second 3 now. But we've now got a lot of pencil marking. We've only got one unpencil marked circle, and we know the sum of all the circles is 45. So we've got 6 there, 15, 21, 24. So these 3 circles have got to add up to 21 to get to 45 overall. So if that's a 5, these have to add up to 16. That's quite difficult. That would have to be a 7, and this would have to be a 9. But if that's 9, these have to add up to 12, which can't be double 6. So this cannot be 6 by dint of logic. That's beautiful. That's beautiful, isn't it? So what I'm saying is, because I know those 3, let's just highlight them. Because these have to sum to 21. If this is 6, these have to sum. Well, hang on. Why did I think that didn't work? 21. Yeah, no, it doesn't work. It doesn't work. It definitely doesn't work. If that's a 6, these have to add up to 15. And the only way, you can't do 5 and 10, so this would be 9 and that would be a double 6. So it definitely doesn't work. So this is down to 3 or 9. But we worked out if this was 5, this was 9 and this was 7. But if this was 9, these add up to 12. So this is 3 or 9. So this is a 3. This would be a 3-9 pair. And that doesn't. Oh, that's so clever. Oh my goodness, that's my favourite step so far, and I've loved this puzzle. I've loved this puzzle so far. This cannot be 9, because if it's 9, this is 9. And why doesn't that work? It's this little line here. If that's a 9, what numbers do we put on this? We've got 9 times this digit is equal to 9 times this digit. Well, then those digits have to be the same to make that sum work, and that doesn't work from Sudoku. So it's broken. So this is 5. That's 5. That's 9. That's 7. Now, how's that going to work then? This has to be. It can't be a 14. This has to be a multiple of 7 now, because That's how prime numbers work. That's a facetious way of saying it. But what I'm seeing there is this digit times this digit has to be a multiple of 7, doesn't it? Because we know those two digits are a multiple of 7. And I can't write 14 in there, so I think I've got to write 7, and then that becomes 9 by sort of the dint of the mathematics. And that's not 7 anymore, which I can't remember. That was something to do with 2 and 7 here, wasn't it? I will come back to that in a moment. Let me just think about this again. Okay, do I now know what these are? 36 was sum. So yeah, these have to sum to 4, so they are a 1-3 pair. That's really annoying. That doesn't do anything. Does it do anything? 5? No, I thought maybe I could do something with 5. No, okay, I don't know then. Oh, maybe it's prime factors again, is it? Maybe on this line. All I'm thinking again is that these two digits, we know that those two digits times this digit are a multiple of 7, don't we? So we're going to need these two to sum to a 7, a number that's a multiple of 7, which could be 7 itself. So it could be a 1-6 pair. It couldn't be 3-4, and it couldn't be 2-5, or it could be 14. And if it's 14, it would be 6-8, because it couldn't be 5-9, and they can't add up to 21. So I think that there is a 6 in those squares. That would be my conclusion there. But hang on. Am I going mad here? I might be going mad. If this was 14, don't those have to add up to 18 then? I can't do that. That's too big. That's what I'm sort of feeling there. Because if this is 2 times 7, which it would be, yeah, 14. Oh gosh, it's really weird when you do these things on camera. You sort of, you corpse a bit, if that makes any sense. Yeah, 126. 126. That's got to be 18. It doesn't work. Yeah, this gets too big. So that means this is not adding up to 14. It must only add up to 7. So in fact, that is a 1-6 pair. And now these have to sum to 9, I suppose, is the corollary of that, and that's not very useful at all. It's obviously not 2-7, but it could be 1-8, 4-5, or 3-6, I think. Okay. All right. What are the other digits here then? 2, 3, and 8. Oh no, I want to put those in the middle of the cells. 2, 3, and 8. Also not useful. We've got. Oh, I don't know actually. I'm not sure now. I would. Oh yes, I could come back and think over here. I removed 7 from this square, which. So if this was 18, if that was 6, how am I making this work then? That can't work anymore, can it? Because if this is 6, let's just do this slowly. We've got 18 is the product here. So these two squares, yeah, it doesn't work. It doesn't work. We can't do it anymore because 7 has come out of here. Because these two multiplied by this digit, the sum of these two multiplied by this digit need to equal 18. So if this is 3, that would need to be another 3. That doesn't work. And if this is 2, we worked out that needed to be 7. So now we can write, what was the other option? 4. This is a 4. Don't tell me that does nothing. So now I know I'm going to 12, I suppose. This probably can't be 3 now. Yeah, because this is at least 6. So this is 2. This is 3. And therefore this is 1, I want to say. Yeah, because it's the sum of these numbers times by 3 that's going to give us the 12 that we're looking for. So now this is... let's just be careful here. These have to be a 1-3 pair, don't they? Because what we're saying is we need 6 times 2 to equal the 12. So that has to be 1, that has to be 3, and we get loads of digits. And there's a chance of 3 in the corner here. Oh, now I really want to use those 2 digits. Is that fair? All I'm thinking is that those 2 digits are multiplied by 7, aren't they? To get to these, the sum of those digits multiplied by 2. Now 7 is prime. So in order to get this to be a multiple of 7, these two are going to have to sum to a multiple of 7. Now we can't make them only add up to 7 anymore, because 1, 6, 2, 5 and 3, 4 are not available. So they have to add up to 14. Which might be possible either way round. It means they're either 5, 9 or 6, 8. That's not 6, so that's not 8. And 14 times 2 is 28. So these have to add up to 4. I mean, there's no... Yeah, they can't add up to 21. Let me just play around with this for a moment. I think these have to sum to 4. I think they have to be a 1-3 pair. And that's really beautiful, because this 1-3 thing means that we've got 1-3 pairs here. This is going to be a 6. That's going to be a 1. The 3 can't be in these positions anymore. So this has become a 3. I'm sure this is useful. Let me just think about it. No. Oh, maybe it's though. Yeah. Beautiful. Yes, it is beautiful. Although it doesn't resolve. Okay, but I do know. We worked out, didn't we, that these had to sum to 9, I think. Because we've got 7 times 9 here. So we've got 7. These should be adding up to 9. They're not 1, 8, they're not 3, 6, they're not 2, 7, so they are 4, 5. So these squares are 2, 6, 8. Let's just write that in. That's not 6. Or 2. That's actually an 8, apparently. So we get a 2, 6 pair at the top. Oh, this is good. That's a 6 by Sudoku. So 6 has come off this line, which must now be a 5, 9 pair, adding up to 14. So now we need 4, 7 and 8 into these squares. But can we do better over here? I think we might be able to. That's now a 2. That's now an 8. I'd love to resolve... Oh, I know the digit at the bottom of the grid. That's a 5 by Sudoku. 4 is in one of those squares. Oh, look, see that? That digit wobbles around when we put the 4 in. That's one of the peculiar things of the world. Yeah, okay, so we can keep doing this factor, the prime factor idea, I think. Look at those 2 squares. Now, we know that the sum of these squares times by 2 is equal to the sum of those squares times 3. So these 2 must sum to a multiple of 3. Otherwise, the numbers will not work. So 4 and 7 would be 11, which just doesn't work. There's no multiple that we could put on here. So there must be an 8. There must be an 8. This is great. There must be an 8 on this domino. And it could be 8, 4. That's 12, which is a multiple of 3, or 8, 7, 15 is a multiple of 3. But the fact that there's an 8 on here, we actually could place the 8. Yeah, that does absolutely nothing. But it was quite exciting for a moment. Oh, I'm sorry. Okay, let's try those squares. Oh, this is a naked single. 2, 4, and 5. It's got a 4, 5 in the column, so that's a 2. So this is 4 or 5. That 5. Oh, that's been a 9 for some considerable time, but is it doing anything is the question, and the answer is no, I think. So 1, 6, 7, 8 into... So this is a naked single. That digit C is 6, 8, and 7. So that's a 1. And we need to put 6, 7, and 8 into the gaps here. 6, 7, and 8. I've just noticed we're not getting... Oh, no, we're no Christmas threes again. Christmas threes have been hard to come by of late. 2, 6... come on, Simon. What's going on now? How many lines? We don't have a great many lines to use, do we? That 3 is resolving this 3-1 thing that was going on earlier, so we can do a bit of Sudoku there. So 1s, are they? No, nearly. We can nearly do some clever things with 1s, but not quite. So maybe we've got to do our factorizing trick down here, do we? These have to sum to a multiple of 5. But I mean, they could be 5, 10, 15. That doesn't feel very useful. 6. Yeah, okay, where's 6 in this row? That's a good question, I think. If I put 6 on this line, that's absolutely great in the sense that we do need these to sum to a number that's a multiple of 6. But what would be the other digit that would accompany the 6 on this line? That's quite a good question. So let's say we put 6 there. So we've now got 30. Which sounds great, but we need to make sure that we preserve the multiplicivity or something of 6s here. So this needs to either be 0 or 6 or 12 or something. It can't be anything. It can't be anything, and preserve the logic. You just can't put a 6 on this line. It's very strange, but it's true. So 6 in this row is there. That's got to be 6. That's got to be 2. Now these squares are 7 and 8, which apparently is not resolved. Those squares are 2 and 4. Now, what's that done? The answer is... I don't know. I don't know. Okay. Okay, so we have to look somewhere else, I think. I'm tempted to pencil mark this one. I'm not sure. Everything so far has been so pure and beautiful that I feel that it's probably worth me just spending a moment thinking about this rather than ploughing into it in an ill-considered way. 6 could be 2, 4, couldn't it? I can't see why that's impossible at the moment. 4, 4, 8 maybe. Maybe there has to be a 4 on there. I'm not sure that matters though, even if it's true. Okay, let's think about this then. Yeah, okay, I'm going to pencil mark it. What do we need? We need 2, 5, 6, 9, just from a Sudoku perspective. Now we can get rid of 6s from there, we can get rid of 2s from here. And we need these to add up to a more... No, we can do it. I think we can do it in a few different ways, actually. Maybe it's the actual numbers themselves, in the sense that if that's 7, where are we going to then? 56 times 2, 112. Yeah, okay. 112, 3. Oh no, that doesn't. Hang on. Have I just done my maths wrong? I must have done my maths wrong there, I think. Oh, it's not. I'm not. Hang on, what did I do there? I multiplied them all. Oh, good grief. I was thinking this doesn't work at all. I couldn't make the maths work, and that's because, no, we've got to sum these, don't we? Oh, goodness. I hope I haven't done that. I could have done that earlier and not realised. Let me just think about that for a moment. Yeah, no, I said the sum of those had to be divisible by 3. That's true. I don't know why I just suddenly multiplied all these together. It's because I've gone mad. Okay, so we sum these. We don't multiply them together. So we've either got 24 or we've got 30. So, oh, that makes the maths a lot easier. Oh, that's good. Oh, 8. So this could be 6 and 2. Or these add up to 10. Oh, they can't. They can never involve 5 then. They can never involve 5. And we can't... Yeah, hang on. How could we make these? There's no way to make this add up to 10. Yeah, so this is very much simpler than I was making it. So I was trying to multiply everything together in this box, and that's nonsense. So I'm just going to double check it. 15 times 2 is 30. 12 times 2 is 24. That's a 3. So these either add up to 8 or 10. And there's some reason. Is there? Why couldn't that be an... Why? Oh, it can't be. Yeah, there's no 10 domino available. 1, 9, 2, 8, 3, 7, and 4, 6. So it's that simple. So this is 6. This is 2. It's the only way to make that work. And that is therefore 24, which means this is a 4. That's a 7. That's an 8. That probably does a lot more than that, actually. But let's just think about it. So 2... This becomes a 5, 9 pair. So 9 in this box is placed. It's got to go there. That means that's 9. That's 5. That's 4. That's 5. That's 6 or 7 by Sudoku. That's 4 by Sudoku. So that's 5. And we can now... can probably do a lot of things, but I'm just trying to see the easiest thing to do. And I'm failing, I think. Oh dear. Okay, so what do we think then? Is it going to be some Sudoku-y nonsense? It could be. 4, 5, 7, 9. That's 4 or 5 by Sudoku. See 7 and 9 in the column. 5, 7, 9. 3, 5, 8, 9. Oh, nearly. I think that's 5 or 8. 3, 5, 8, 9. Okay, maybe this isn't how to do it. Maybe it's not Sudokuable quite. Let's have a look at this column. 1, 4, 7, 8 into those squares. That's so annoying. This one isn't restricted at all. This is the one you want to get restricted, isn't it? At least I'd like to get it restricted. Okay, so let me try something else. Is it going to be this line down here? These have to add up to a multiple of 5. And that cannot be, well, it can't be 1 and 4 because this can be neither of those. It might be able to be 2 and 3 though. If that's 2 and that's 3, does that cause a problem with anything? Maybe it's harder for this to be a multiple of 6. I'm not sure. Let's have a look at this digit. 1, 2, 4, 7, 8. Oh, 1. So 2, 7 or 8 into this square only. So this could be a 2-4 pair. Or it can be a 4-8 pair. It can never involve 7. That is definitely true. We can't make 18. We can make 12, but only with 4-8. And we can make 6, but only with 2-4. So this is, that's always a 4. I mean, that's hard to see, actually. That was hard to see. I think I got to that earlier as well. I just didn't follow up on it. So this is 7, 8. That's a 1 at the bottom of the grid. Therefore, I feel like all the 1s are done. And that is going to seriously restrict what this can be, I think, if we bother to think about it. But let's try first Sudoku, in case we get lucky. 2, 7 and 8 into those squares. That's not available to be 8. That's not available to be 2. Right, okay, so let's now try and work this out. So if this was 8, then we're looking at 60 here, 12 times 5, which means these would add up to 10, which would be, so that's 8. This would be an 8 or a 3, I don't believe it would be 3 or 8. I think maybe both of those work. If that's 2, we're looking at 30, aren't we? And then these would add up. That doesn't work. Oh, beautiful. If that's 2, that has to be a 2 as well. Because we've got 6 times 5 is 30. So these have to sum to 5. And that can only be a 2. It sees 1, 4 and 3, so that we get 2 2s in a row. That's lovely as well. So that's 8, that's 8, that's 7, that's 7. Actually, hang on, that's now 7 by Sudoku. So that's 2 and that's 8 by Sudoku. That's 8 by Sudoku. Just following through on our pencil marks. That's a 6 in the corner. That's going to do some work. In this column, we've not placed 2 and 3, which apparently is still unresolved. But we must be able to do a little bit. Oh, yeah, where's 5 in column 6? It's there. That might have been available for ages. I've just not seen that. So that's 4, that's 4, that's 2, that's 2, that's 3. Reiterating our lack of 3s in the corner. That's a 9. And that's 5, that's 9. 9 goes here, 3 goes here. We need 4 and 7, so 4 in the middle of the grid today, and 3 and 5 down here. What a brilliant puzzle that is. I absolutely love that. The step in the middle where we worked out that this line would contain the same digit. I think if that was a 9 or something, that was so clever. It's not of me, of BenTen. BenTen, take a bow. Your secret squared. Your secret is not safe with us, but your secret squared was an absolutely magnificent puzzle. and a really fantastic forerunner to the new year, which hopefully will be full of Sudokus of this quality. Let me know in the comments how you got on with the puzzle. I enjoy the comments, especially when they're kind, and we'll be back later with another edition of Cracking the Cryptic.